We've talked about parallel resistance and we've talked about series resistance. Now what we want to talk about is combinations of resistors. So in some cases we may see a mix of series and parallel configurations, and that's what we're seeing here. Here's our battery, and here's a series of resistors, and here's another series resistor, but they are combined in a parallel circuit. So what we have to do is look at the resistance of each branch and then calculate those as a series circuit and then look at it as a parallel circuit afterwards. So what I'm really saying by that is what these circuits are is this is two series combinations in parallel with one another. So add these in series, so add this one, R1 to R2, and then add R3 to R4. What you'll then do is say, well, we have series combination 1 and series combination 2 added together, and then add those using the inverse rule. So this would be R1 and R2, this would be R3 and R4. So the total resistance of this circuit would be parallel in terms of 1 over the total resistance would be 1 over R series combination 1 plus 1 over R series combination 2. So let's take a look at this. Here we've got the exact same situation we just saw, just with numbers attached. So here we have a 3 ohm and a 2 ohm resistor. That's in parallel with another series circuit of 6 ohms and 4 ohms respectively. So our total resistance here for this branch is 3 ohms plus 2 ohms, which gives us 5 ohms in total, and a total resistance for this branch will be 6 ohms plus 4 ohms, which will give us 10 ohms. Now we've done that, we can add those two parts of the circuit together using our reciprocal rule. So now 1 over the total resistance will be 1 over 5 from here plus 1 over 10 from here. That'll give us 1 over 0.3, which will give us a total resistance of 3.33 ohms. So taking a look at a slightly more complicated circuit now. So here is our battery again, as is tradition, to provide us with voltage. We now have a 20 ohm resistor here in series with the battery, and then we have a combination here of two resistors in series with one another to another resistance in parallel. So how do we deal with this? Well, here's our circuit redrawn, and what we're going to do is first find out the resistance of this branch, branch 1. That's 30 plus 10 ohms, which gives us a total of 40 ohms. That is in parallel with a 40 ohm resistor. So 1 over 40 now plus 1 over 40 will give us 1 over 0.05, which will give us a total of 20 ohms. This part, of course, you can see winds up being halved. So if this was two 40 ohm resistors, you'll have an effective resistance of 20 ohms. Now, this 20 ohm resistor here is in series with all of this. So now what we have is a 20 ohm resistor in series with an effective resistance of 20 ohms, which gives us a total for this circuit of 40 ohms of effective resistance. Now, I'm going to show this example, but one student once got particularly upset with this example, and I'll tell you why. Now, you can use an analogy of a toll road, that if you have 3 lanes of vehicles, or actually, yes, 3 lanes of vehicles here, and they all have to come down to 1 lane to go through a toll booth and then go back to 3 lanes, then your resistance here is whatever it takes to go down to 1 lane and then back to 3. Now, if you took 3 resistors in series, that would be like having 3 toll booths, one after the other after the other. And this is where one particular student had a bit of a meltdown, saying, well, why would you want 3 toll booths, one after the other after the other? And I said, it's an analogy. Okay, there's 3 things that slow the traffic down, to which they were still upset about the toll booth. So I said, okay, fine. This is a toll booth, this is a hot dog stand, this is an ice cream stand. To which the response was then, I don't like hot dogs or ice cream. I don't care. You're going to stop at each one. So as you come down from being 3 lanes to a single lane, you will experience resistance at each of these stations. Given the current situation, this is probably customs, this is coronavirus testing, and this is quarantine. That works better. So this is your series case. In terms of parallel, well, here's 3 vehicles, 3 lanes coming in. If these vehicles split and go through 3 toll booths, then the traffic is split equally between all 3 of these resistances. I didn't say it was a good analogy. It's an analogy. So, if you add toll booths in series, you increase resistance and slow the current flow. If you add them in parallel, you will lower the resistance, but still have some, but increase the current flow. That's what you should take away from it, not toll booths and hot dog stands. So there is a distinct advantage of a parallel circuit. And we said for a series circuit, if we had 3 bulbs in series and one of them stopped functioning, one of them blew a bulb, essentially blew their filament, then there's no longer an electrical connection and the whole circuit will stop functioning. In a parallel circuit, we have 3 pathways for our electricity, and here we've got a battery supplying electricity to 3 bulbs. Now, if we were to remove a bulb, here brutally with a hammer, the other 2 bulbs will continue to function, as these 2 pathways will be completely unaffected. So that's an advantage of a parallel circuit over a series circuit, and how to add their respective resistances. While we are discussing the addition of resistances, I just want to take a moment to go back. We already talked about capacitance and said capacitors store charge, and we often calculated exactly how they store charge and how much charge they would actually store in terms of C, capacitance, and C was Q over V. C was also epsilon A over D. And remember our capacitors, as we said, they stored charge for us. But remember the addition rules here were flipped compared to those of the resistor. In the case of the resistor, 1 over R applies to a parallel configuration. In the case of a capacitor, 1 over C applies to a series configuration. So make sure you don't get these backwards. Series is opposite in terms of capacitance than resistance. If we were adding resistors in series, we would just add R1 and R2 and R3. If we're adding capacitors, it's 1 over C1, 1 over C2, 1 over C3. So for capacitors in series, it's inverse. For capacitors in parallel, you simply add them. So these rules are opposite for resistors. Don't mix them up. So that's resistors. We've recapped capacitors. What about batteries? What happens if we put batteries in series rather than parallel? Well, if we hook up our batteries in parallel, what we're really doing is taking all the positive terminals and connecting them together, and all the negative terminals and connecting those together. Effectively, what will happen here is this battery will charge this one will charge this one, and this one will charge this one. That means each battery along the line is charging up the next, and the total output from this battery pack will end up being 1.5 volts. Now, that isn't a great way to boost the voltage, but it is a great way to make a very long-lived battery pack if all you want is 1.5 volts. Now, say we take our 1.5 volt batteries now, 4 of them, and string them together now in a series configuration. And by series, what we're going to do is take the positive terminal here and connect it to the negative terminal. Positive to negative, positive to negative, positive to negative, and then connect back to the negative for our circuit to be made. If we do that, we'll have 1.5 plus 1.5 plus 1.5 plus 1.5, and we will get 6 volts out of this system. So here, if we arrange our batteries in series, the voltage will be additive, and we'll end up with 6 volts coming out and a shorter lived system at higher power. But if we have them in a parallel configuration, we will only get 1.5 volts out as each battery charges the next. Now if we show that as a diagram, here's our line, long line, short line, long line, short line, all connected together in a series configuration, with a similar diagram for our parallel case. So the thing to remember here is for batteries in series and parallel, for the series case, the voltage is increased. For the parallel case, there's no change in the voltage of a single battery. So if you hook together 4 1.5 volt batteries for the parallel case, you will still get 1.5 volts out of the other end. But it'll be a long-lived battery pack.